why we are going to discuss this ripple carry adder design? So basically, if you observe in the half adder and full adder, we are able to add only one bit of data. So in the case of full adder, the width of your A and the width of your B is only one bit. Okay. But if you want to add more than one bit of data, then you need some other design. Okay. So this is nothing but your ripple carry adder and carry lookup adder, and we have several lot of adders. Yeah. Okay. So this is the two type of adders which we are going to discuss. One is triple carry adder and carry lookup adder. Okay. So using this type of design, we can add more than one bit. Okay. So a n bit triple carry adder. So we can add n number of bits. A n bit ripple carry adder RCA will have n full adders. Okay. Basically, it is going to have n full adders. Okay. Let's say suppose if we want to add 4 bits. Okay, let's say if we want to design a 4-bit RCA, then how many full adders we are going to have? We need 4 full adders. So let's say suppose if we have two values, one is A and another is B. Okay, so let's say A value is 1100 and B value is 0011. We need to add this two, and let's say initial carry is seen is equal to 0. Okay, so we need to add A which is equal to 1100 and B which is equal to 0011 and seen is equal to 0. We need to add this three things. Okay, so the width of A is 4 bits and the width of B is 4 bits. So you cannot take only single full adder to add this A and B. No, we cannot take only single full adder. We need a 4-bit triple carry adder. Okay, so in the case of 4-bit triple carry adder, we are going to take 4 full adders. Okay, so let us try to see the design of 4-bit triple carry adder. 4-bit RCA. Let us try to see this 4-bit RCA design. So as discussed, this 4-bit RCA is going to have 4 full adders. Okay. So let's say this is MSB, this is A3, this is our MSB, and this is A0, which is our LSB. Okay. I will write down here. So A3, A2, A1, A0, where A3 is our MSB and A0 is our LSB. So how to write this? So A3, A2, A1, A0, which is equal to 1100. 1100 and followed by B3, B2, B1, B0. What we have taken? So we have taken 0011. 0011, and this is our MSB and this is our LSB. So this is MSB and this is our LSB. Okay, so this is our MSB and this is our LSB. Now, so let me draw the 4 full adders. So 1, 2, 3 and 4. So these are our 4 full adders which I am taking. Okay, so this is my LSB. So this is my FA0, this is FA1, FA2, FA3. Okay, so here I am going to apply A0 and B0 and A1 and B1, A2, B2, A3 and B3. So where A3 and B3 are my MSBs and A0 B0 is my LSB. And here I am going to give my scene. Okay. Now here I am going to get my S0, S1, S2 and S3. So like this I am going to get my S0, S1, S2 and S3. Now from each full adder I am also going to get carry, right? So the carry which I am getting from my full adder FA0, I am going to give it to the next stage. Okay. So let's say this is C0. Now the carry which I am getting in FA1, I am going to give it to the next stage. Let's say this is C1. Now the carry which I am getting in this FA2, I am going to give to FA3. This is C2 and this is my final carry which is C out. So this is how we are going to design our 4-bit ripple carry adder. Okay, so this is how we are going to design our 4-bit ripple carry adder. Now, so why we are calling this as ripple carry adder? Why? What is the reason? What may be the reason why we are calling this as our ripple carry adder? Okay, so basically if we observe here, the carry from the first stage is going to the second stage, and from the carry from the second stage it is going to the third stage, and the carry from the second stage it is going to the third stage. Basically carry is like rippling. Okay, so if you see the waves, those are rippling, right? So like that only here the carry is being rippling from one stage to another stage, the carry is propagating from one stage to another stage. Okay, so that is why it is known as carry ripple carry adder. Okay, so here I will write down here the carry is another. Okay, so that is the reason we are calling this as ripple carry adder. Okay, now so let's say suppose if a naught is equal to, let us substitute these values. Let's say a naught is equal to 1, a1 is equal to 1, a2 is equal to 0, a3 is equal to 0, and b naught is 1, 1, 0, 0. So if we add this, what is the reason what is the answer we are getting? So 1, 1, 0, 0, 1, 1, 0, 0, and 0, 0, 1, 1, 0, 0, 1, 1. Okay, 1, 1, 0, 0, and 0, 0, 1, 1. So if we are adding this, so we are getting 1. This is our sum, and 0 1 1 1 0 1 1 0 1. Okay, I will write it with another color. So this is our sum S1, and this is our sum S2, and this is our sum S3, and this is our sum S4. Okay, or S0, S1, S2, S3. And from this is one full adder. So one full adder is making this operations, that is fa naught, and we are getting a carry which is being propagated to the next stage. Okay, and another full adder, that is fa1, is taking care of this addition, and one more full adder is taking care of this third stage addition, fa2, and last full adder is taking care of the last two bits, fa3, and we are getting C0, C1, C2, and finally C3. So this is how we are making the addition. Okay. Yes. So is the ripple carry adder design working? Are they clear? So are there any disadvantages here? Can you find out, or can you see any disadvantage or any drawbacks of this ripple carry adder? So basically this ripple carry adder is uh, basically the speed of this ripple carry adder is less. Okay, it is less speed. Okay, so why, what is the reason? Because let's say suppose this fa1, this is waiting for the carry to be generated from the previous stage. Unless and until the carry from the previous stage has been generated, this fa1 is not going to give you the sum. Okay, and this fa2 is waiting for the carry which is being generated in the fa1 stage. So unless and until the carry which is being generated in the fa1 stage, this fa2 is not going to give you the s2. Okay, and same here also, since fa3 is waiting for the carry that is being generated from the previous stage, so there is a dependency. So I will write down here, due to the dependency on previous stage carry, ripple adder speed is low. Okay, so here this is a one of the drawback of RCA. Okay, yes, so that was about our ripple carry adder. Now let us try to understand our carry look ahead adder. Let us try to understand this carry look ahead adder. So let us try to understand this. Now first of all, before going to discuss about this carry look ahead adder, we need to understand few terminologies here. So let us take our full adder example where we have three bits A, B, and C, and let us take the carry out. Okay, so this is our full adder. This is our full adder where we have three inputs A, B, and C, and we have our C out. Okay, and sum. So I'm going to take my C out and ABC in for my analysis. Okay, so what I'm going to take A, B, C in, and C out. So 0, 0, 0. Why I'm only taking C out? Because in the case of ripple carry adder, I have a problem with my carry rippling. Okay, so that's why I'm taking the C out for my analysis. Okay, 0, 0, 0, 1, 1, 0, 1. So whether we will get any C out here? No. Okay, here the C out is equal to 0. Here also we are not going to get any C out. Here also we are not going to get any C out. Here we are going to get a carry, output carry. And here we are not going to get any output carry. Yes, here we are going to get it. and at this stage we are not. Yes, here also we are going to get, and last stage also we are going to get. Okay, so this is our relation between A, B, C in and C out. Now, can you find out any relation between A, B, C in, C out from this table? Okay, so let me tell you what is the relation, what is happening here. So in this case, if we see, so here whatever the value of your scene, in this case, whatever the value of your scene, your C out is 0. Here if you observe, if C in is equal to 1 also, C out is equal to 0. So here no carry is being generated. So we are not going to consider this case because there is no carry generated. Okay. If no carry is generated, then there is no problem at all. But where is a problem which is happening in the carry generation case? Okay. So A is equal to 0, B is equal to 0. This case we are not going to consider. Okay. And so this case we are not going to consider. Now let us take this case. A is equal to 0 and B is equal to 1. Okay. Now if you see this case, whatever the value of C in we have the same value of C out. So whatever the value of C in we are having, same value we are having. Okay, I will write down here. That is C in is C out is equal to C in. Okay. So this is one scenario. Okay. So whatever the value of C in, we are getting the same value of C out. That is C in is equal to C out. Now in this case, in the next case also we are getting the same. So whatever the value of C in, we are getting the same C out. Okay, here also we are getting the same thing. C in is C out is equal to C in. Now in the last case, I will write down in the next slide. So in the last case, A, B, C in, C out, 1, 1, 0, 1, 1, 1. This is the last case. So here we are getting 1 and 1. So we can observe from here that if your scene may be 0 or if your scene may be 1, whatever the value of your scene, unless it is not going to care about the value of scene, your C out is equal to 1 only. Okay, here your C out is equal to 1. So it is not depending upon the value of scene. Okay, so whatever may be the scene value, so your C out is equal to 1. Okay, so these are the cases which we can see from this table. Okay, the first case we are not at all getting the carry, so we are not at all considering that case. Okay, in the second and third case which we can see, so what is a C out is equal to C in, we can see from the second and third cases, and in the fourth case we have is C out is equal to 1. So whatever may be the value of C in, your C out is equal to 1. Okay, so this is case 1, case 2, case 3 and case 4. Okay, case 2, case 3, case 4 which we are going to focus upon. Okay, so in case 2 and case 3 we have C out is equal to C in. Okay, so in case 2 and case 3 what we have is C out is equal to C in, and in case 4 we have C out is equal to 1. Okay, now let's say so if we have C out is equal to C in, that means I can say my input carry is simply propagating. Can I say my input carry is being simply propagating? Yes or no? Yes. Okay, so in my case 3 and case 4, sorry, in my case 2 and case 3 I can see C out is equal to C in. That means my input carry is simply propagating. Okay, I will write down here. So in case 2 and case 3, carry is propagating. Carry is simply propagating. Okay, carry is simply propagating. So let us call this propagation of carry. Let us label it with P. Okay, now what may be the equation of P? From the truth table we can see A bar B, and what is the min term here? A B bar. Okay, what is the corresponding output I am taking? So here in these two cases this is one, that is A bar B plus A B bar. Okay, so P is equal to A bar B plus A B bar, which is nothing but my A XOR with B. So my carry propagation, can I say A XOR B? So carry propagation can be written as A XOR B. What is carry propagation? Carry propagation means simply input carry is propagating to the output. Okay, so whatever the input carry we are having, same carry is propagated to the output. C in is equal to C out. Okay, now let us try to write down the equation for carry the case 4. Okay, so what do you call the case 4? What can we call the case 4? Case 4 can be called as carry generate. So what do you mean by carry generate? So whatever may be the value of input carry, it may be 0 or it may be 1, your carry is generated. That is, you are getting your output carry. So I am calling this case for as carry generate. Okay. So what will be the equation of this carry generate? You can take the min terms AB plus AB, that is AB only. So carry generate I am denoting with G, that is nothing but AB. So here the carry generate is G is equal to AB. So these are the equations for carry propagate and carry generate. So we already know the equation for your carry, C out. What is the equation of carry which we can write? AB plus C in into A XOR with B. So this is a alternate second equation of our carry in the case of full adder. This equation we have already derived in our previous classes. Okay. So C out is equal to AB plus C in into A XOR B. Now can I say this AB as carry generate? Yes. So can I call this AB as carry generate? Yes. So this is my carry generate, which I will denote it with G. And this is C in into AX or B. I can call this AX or B as carry propagate. Yes, I can call this as carry propagate. That is P. So I can write down this equation as C out is equal to G plus C in into P. G plus C in into. So C out is equal to G plus C in into P. And what is the equation for sum? Sum is nothing but AX or BX or C. There is no problem in the sum. The main problem in the sum is the main problem in the addition was in the case of triple carry was C out. We were getting the trouble with your C out. So that thing we are trying to solve it. Okay. Next. So is this clear for everyone? So let us try to find out the carry for each and every stage. Okay. So the generalized equation which I can write for this equation, this C out is equal to EB plus C in into X or B, I can write it as CI is equal to GI plus PI into CI minus 1. Okay, where here I stands for stage, which stage you are in. Okay, so for example, if we have a 4-bit triple carry adder like this, then this is I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4. If we want the first stage carry, then we will substitute I is equal to 1. If we want the first stage carry, we are going to substitute I is equal to 1. That is C1, which is equal to G1 plus P1 into CI minus 1. That is 1 minus 1, that is 0. So here C naught, which is going to indicate your initial carry. This is your initial carry. Okay. Now, if I want to find out the second stage carry, so what I'm going to do, if I want to find out the second stage carry, what I'm going to do is I'm going to substitute I is equal to 2. That means carry for second stage. So how I'm going to find out the carry for second stage? I can just simply substitute I is equal to 2. That is C2, which is equal to G2 plus P2 into Ci minus 1, that is C1. Now you can say, sir, there is a dependency. We are depending upon the C1. But if you expand this C1 equation which we have calculated previously, then what will happen? C2 is equal to G2 plus P2 into, what is the equation for C1 which we have got? G1 plus P1 into C0. So here there is no dependency upon the previous stage carry, where your C0 is your initial carry. Okay. So like let's say suppose if I is equal to 3, then C3 is equal to G3 plus P3 into C2. You cannot say, sir, it is depending up C3 third stage carry is depending upon the second stage because we are having C2. No, if you expand the C2 equation, C3 is equal to G3 plus P3 into, if you expand this C2, then you will get G2 plus P2 into G1 plus P1 into C naught. So this is also initial carry. So can you see any dependency upon the previous stage carries? Whether the present stage is anywhere depending upon the previous stages? Can you see any dependencies? No. Okay. So there is, in the case of in this particular equations, we cannot see any dependency. So no stage is depending upon the previous stages. Okay. So here there is no dependency on the previous stage carries. Previous stage carry. So this is how we are going to develop our carry look ahead adder. So in the case of carry look ahead adder, we are going to find out the carry depending upon the present values only. If you expand G3, G3 is nothing but A3 and B3, and P3 is nothing but A3 XOR with B3. So A3 and B3 are already given. Okay. And if you expand G2, this is also already given. So everything is already present. So at the same stage only, you are basically generating your carry equations. Okay. So this is how your carry look ahead adder is going to work by generating the carry, and it is not at all depending upon the previous stages. And let me draw the diagram for this. So this is CLA carry look ahead adder. So it is going to have inputs as G3 and P3, G2 and P2, G1 and P1, G0 and P0. Okay. And here the initial carry that is we are going to give, that is C0, it is going to be given to this, and at the output we are going to have C3, and on XOR gate we are going to take P3 XOR with this output, we are going to get S3, and P2 XOR with the output of your XOR gate, this is S2, P1, S1. So this is how we are going to, and P0 and C0 from here we are going to take. Yes. So this is how we are going to develop our carry look ahead adder. Yes.